So in the previous video, we learned that any system of equations could be represented and stored much more efficiently using matrices and vectors, specifically using a coefficient matrix and an augmented matrix for that system. We also saw yesterday that the actions that we take as we are solving a system of equations, there is a corresponding action that can be performed on the system's augmented matrix. Typically some combination of shuffling rows around, scaling rows, and adding one row to another. And from a computing point of view, performing these actions on the augmented matrix is much, much more efficient than performing these actions on the system of equations. So we much preferred to perform the actions on the matrix and to deal with the matrix as opposed to dealing with the original system. So in this video, we are going to define an algorithm and a process for working with matrices, which is called Gaussian elimination, which is sometimes also called row reduction. And spoiler alert, the process of Gaussian elimination, the process of row reduction, is really just process and the steps that were applied to the augmented matrix as we solved this system of equations. So some terminology. The first thing that we need to define so we can speak about Gaussian elimination correctly, the first thing that we need to define is what's called a pivot of a matrix. And when you're dealing with a matrix, a pivot is just the very first non-zero entry that appears in a row of a matrix. So for example, if I have a matrix that looks like this, 1, 4, 0, augmented with 3, 0, 1, 1 augmented with 2, and 1, 0, 4 augmented with 4, then this matrix would have 3 pivots. The first pivot would be located right here because this is the first non-zero entry in the first row. The second pivot would be located right here because this is the first non-zero entry that you get when you look into the second row. And the third pivot of this matrix would be located right here. This is the first non-zero entry that you see as you read into the third row. So these are 3 pivots for this particular augmented matrix. You could also, for example, consider a non-augmented matrix. So something like let's say 0, 0, 1, 0, 2, 0, and 0, 0, 0. This particular matrix would only have 2 pivots. This first pivot here, 1, being the very first non-zero entry in the first row. This pivot here, 2, being the first non-zero entry in the second row, but the third row doesn't have any pivots in it because the third row contains only zeros. It doesn't contain any non-zero entry. So this guy has 3 pivots, and this guy has 2 pivots. So this is the meaning of the word pivot as applied to a matrix. And we say that a matrix is in row echelon form if it satisfies the following 2 properties. So the first property that must be satisfied in order for a matrix to be in row echelon form is that if you have a row that is full up with zeros, if the row only contains zeros, all of those have been shuffled to the bottom of the matrix. The second property that must be satisfied by any matrix that's in row echelon form is that the pivots have to be ordered in a certain way. The pivots of each row must be to the right of the pivots in every higher row. So let me show you an example of that. Show you an example of a couple of matrices that are in row echelon form. So here is a matrix that is in row echelon form. If I give us something like 3, 2, 1, 0, 1, 0, 0, 0, 3. This matrix is in row echelon form. First of all, what's going on with rows containing only zeros? Well, this matrix does not contain any rows that have all zeros in them, so I don't have to worry about this condition. But let's see what's going on with the pivots that are in this matrix. So in this matrix, I have a pivot located here in the top left. That's the first non-zero entry in the first row. We have a pivot here dead center. This is the first non-zero entry in the second row. And we have a pivot here in the bottom right corner. This is the first non-zero entry in the third row. So notice how these pivots are staggered. As I move from one row down to the next pivot is to the right. And so that is what we mean when we say the pivot of each row is to the right of the pivots that are in higher rows. It has this sort of triangular diagonal quality to how the pivots are distributed in the matrix. Here would be another example of a matrix that is in row echelon form. If I had something like 4, 0, 0, 0, 0, 1, 0, 0, 0, this would also be a matrix that's in row echelon form. I do have a row here that has all zeros in it, but we can see that that has been shuffled all the way to the bottom of the matrix. We have a pivot here in the top left corner. We have a pivot here in the third entry of the second row, and we can see that that pivot is located to the right of the pivots that are above it. So this would also be in row echelon form. One final example, it's also possible to have multiple rows that have lots of zeros in them. So you might see something like 1, 2, 0, 1, 0, 0, 0, 0. And this is also in row echelon form. We've got two rows that have all zeros, two rows that have no pivots, and those are shuffled all the way to the bottom of the matrix. The two pivots that are present in this matrix, this one and this one, are ordered so that as we move down into the next row, the pivot is to the right of the pivot that was above it. So this matrix is in row echelon form as well. For some counterexamples, for some matrices that are not in row echelon form, for example, if we had a row of zeros that was on the top, this does not count because any row that contains all zeros is supposed to be shuffled to the bottom of the matrix. For another example of a matrix that's not in row echelon form would be something like 0, 1, 1, 0. This would not count because the pivot in the top row is further to the right than the pivot in the bottom row. So this is the violation of that property that pivots are supposed to move to the right as you move down the matrix. Here is another matrix that cannot be counted as in row echelon form. If we had 2, 1, 1, 2. This would also not work because these two pivots are directly on top of each other, and this is not permitted. The pivots have to be strictly to the right as we move down the matrix, so the pivots cannot be directly on top of each other. So these might seem like strange rules, but the reason that we have defined row echelon form in this way is that row echelon form is meant to capture the appearance of the coefficient matrix slash the augmented matrix for a system after the process of elimination has been applied to the system. So for example, if I go back to the previous lesson, when we were solving this system of equations by method of elimination, we did the usual elimination steps to the system. We tracked the corresponding effect on the augmented matrix on the right-hand side. And when we look at the augmented matrix that we obtained on the right-hand side, notice that this matrix is in row echelon form. This matrix has two pivots. One of them is right here and one of them is right here. And those pivots are organized so that the pivots go to the right as we move down the rows of the matrix. So this guy has ended up in row echelon form automatically as a result of the steps that we took as we were solving this system. The same thing is true for the second example that we did yesterday. As we solved this second system of equations, the system that was inconsistent and had no solutions, as we applied the method of elimination to the system and we tracked the corresponding effect on the augmented matrix, at the end of the day, once again, we ended up with an augmented matrix that was in row echelon form. The pivots of the matrix are located, in this case, here and here. And so we can see that those matrices, those pivots have that relationship, that this pivot is further to the right of this one. And the same thing was true in the third example that we worked on yesterday. When we were doing this system of equations that was underdefined, and we solved that system of equations, and then we performed the corresponding actions on the augmented matrix, we ended up in this case with a row that contained only zeros. But that row that contained only zeros was on the bottom of the matrix. So this augmented matrix ended up in row echelon form as well. So that's really all that row echelon form is trying to do. Row echelon form is just trying to capture some of the properties of an augmented matrix that you get after applying the steps involved in method of elimination on the system. So let me go ahead and demonstrate the process of performing Gaussian elimination / row reduction on a given matrix. So for example, someone gives me this matrix that has 4 columns and 3 rows and asks me to perform Gaussian elimination. So essentially, they're asking me to take this matrix and write it in row echelon form using the 3 elementary row operations that we established in the previous lesson. So using some combination of swapping rows around, scaling rows, and adding one row into another row, get this matrix into row echelon form. Put yet another way, pretend that this is the augmented matrix corresponding to some system of equations, and solve that system of equations using method of elimination. Except don't do method of elimination on the equations, which are complicated and clunky as a result of having all the variables inside of it. Instead, do the equivalent steps just on the matrix that contains the actual values in the problem. So step number 1, I'm going to go into the top row here, and I'm going to look for a pivot. So I see, for example, here, a pivot in the first column, 1. Now, to get into a row echelon form, I need to make sure that there are no pivots directly underneath this 1. All the pivots in subsequent rows have to be to the right of this 1. So I'm going to try and wipe out these values underneath 1 in the first column using some combination of the elementary row operations. Eliminate the pivots underneath 1 in the first column. If you think about this through the lens of solving a system of equations, what we're essentially doing when we are eliminating these pivots underneath 1 in the first column is we're trying to eliminate the x's from the second equation, and we're trying to eliminate the x's from the third equation. So this is analogous to what we did at the end of our method of elimination review, where we eliminated the x's as our first step in that solving process. So to that end, thinking about the actions that I have and the tools that I have in my disposal, I am permitted to scale rows, and I am permitted to swap rows, and I am permitted to add one row to another. So what I'm going to do is I'm going to scale the first row, and I'm going to add a scaled copy of the first row into row number 2 with the objective of eliminating this 3. So once again, this is analogous in terms of the method of elimination to scaling the first equation and adding it down into the second equation to try to eliminate the x's from that equation. So in this case, if I want to get rid of this 3 here, I need to take row 1 and I need to scale it by minus 3. I can scale row 1 by minus 3 because that's going to turn this first entry into a negative 3. And that negative 3 and that positive 3 will become opposite terms that cancel out when we add the rows together. So scale row 1 by minus 3 and then add into row 2. Now, for the sake of compactness, for the sake of simplicity, I'm going to do both of these actions in exactly the same step here. So 1 times negative 3 plus 3 result 0 as desired. I'm now going to perform exactly the same action on this second entry. I'm going to go ahead and take this number 2. I'm going to multiply 2 by negative 3. 2 times negative 3 gives me minus 6. And then I'm going to do minus 6 added to minus 2 directly underneath that entry. And that's going to give me a value of minus 8. So just as a side note, just to help us to keep track of where this particular entry came from, this came from this 2 right here times the scaling factor minus 3 and then added into this minus 2 down here in the second row. That's where this minus 8 came from. So now let me clean up some of those notes because this is going to get really messy if I make too many notes during this calculation process. I'm going to perform the same action on these third entries here. I'm going to scale this entry in the third column by minus 3. And then I'm going to take that value and I'm going to add it down into the second row. So 2 times minus 3 gives me negative 6. Negative 6 plus 1 gives me minus 5. Finally, for the last entry, if I take the entry number 5 at the end of row 1, and I multiply 5 by minus 3, that gives me a negative 15 in that position. Negative 15 combined with minus 6 gives me a total of negative 21 in that position. So here I've scaled row 1 by minus 3 and that added it into row number 2 here. Let's do the same thing for the third row to eliminate the pivot in this position in the third row. I'm going to scale row number 1 by a factor of negative 2. Because if I scale row 1 by negative 2, then that's going to turn this 1 into a minus 2, which will cancel out this positive 2 down here in the third row. So this will eliminate the pivot from that position, effectively canceling and eliminating the x's from the system of equations. So if we perform that action of scaling the first row by minus 2 and then adding those values into row number 3, so this 1 times this minus 2 plus this positive 2 gives me 0 as desired. Then let's see what happens in the second entries. If I take this 2 and multiply it by minus 2, then that gives me negative 4 at this juncture. Then that negative 4 gets added down into positive 1. So negative 4 plus positive 1 gives me minus 3. And then moving to the third column, this entry in row 1 times this minus 2. 2 times minus 2 is negative 4. Negative 4 plus this negative 1 gives me minus 5. So we have this 5 times this minus 2. That gives me negative 10. And that negative 10 gets added to minus 1, giving me a result of negative 11. So if we're then continuing through the Gaussian elimination process, the next thing we do is look at the next pivot in the next row. So the next pivot present in this matrix is located right here in the second row, this pivot here of -8. And in order for the matrix to be in row echelon form, we need to make sure that there are no pivots directly underneath this -8. Any pivots in the rows underneath row 2 have to be off here to the right-hand side. So we need to eliminate this pivot of -3 that is located underneath -8. So to that end, I'm going to try and scale these rows so that when I add them together, this -3 cancels out. So I'm thinking about, okay, what do I need to do to transform a -8 into a +3? Because if I can transform a -8 into a +3, then that +3 will cancel this -3 in this lower position here. So for example, I can scale row 2 by the quantity -3/8. Because if I take -8 and I divide out 8 and I multiply by -3, that'll turn this value into a +3. Once that's done, we can add that down into row 3. And that will eliminate the -3 in this position. So first of all, if I perform this process on the first entry in row number 2, if I take this 0 and I multiply that 0 by -3/8, then it's still going to be 0. And so when we add it into row number 3, it's not going to have any meaningful effect. There's still going to be a 0 in this position. And that's important because we do need to make sure that there are zeros in this first column, that there are no additional pivots in this first column. Now, by design, when we take row number 2 and we take that -8 and we multiply it by this number, it's going to turn that -8 into a +3. And so that +3 in this position, when we add it to this -3, is going to cancel out and it's going to cause a 0 to appear in this position. So the real challenge in terms of the arithmetic is going to be these last two entries. I'm going to have to take the -5 from row number 2. I'm going to have to multiply it by 3/8 negative, and then I'm going to have to combine that with the -5 that is here in the third row. So when I perform that action, I get 15/8 minus 40/8, giving them a common denominator. So this is -25/8 if I've got that arithmetic right. So this would be the entry that ends up in this position. And let's perform the same action in the fourth column of this matrix. So I have to take this -21, I have to scale it by this value, and I have to add it to the -11 in the next row. So let's go ahead and perform that. -21 times -3/8 plus -11 in row number 3. So that's 63/8 minus 88/8, if I've got that correct, -25/8. So that's the value that would end up in this position in this particular matrix. We have, as of this moment, obtained a matrix that is in row echelon form. You can confirm that by looking at the pivots. Here's the pivot in the first row, and down and to the right is this pivot in the second row. Down and to the right is this pivot in the third row. So this matrix is now in row echelon form, so we can stop the process here and use this as a final answer. So that's Gaussian elimination. Gaussian elimination is the method of elimination from 2 videos ago, except instead of being applied to a system of equations, it's being applied to a matrix that is representing that system of equations. The idea of the process is to scale rows and add them together, starting in the first column with the first pivot, trying to eliminate and cancel out all of the pivots underneath that entry. So notice that the process does work through the matrix from left to right. We start always in the leftmost column with the pivots in the leftmost column, and then we eliminate the entries underneath that. Then we move to column number 2, look for the pivots in column number 2, eliminate those underneath. Then we move to column number 3 and column number 4, and so on. We go from left to right to get this beautiful pattern of zeros in the bottom left corner of the matrix. One more example of this process in action, just to give you an example of a situation where I think I would actually use the operation of swapping rows. Someone says perform Gaussian elimination on this matrix, and when I am asked to use Gaussian elimination, I'd love to shuffle rows that have ones in them directly to the top. So let's go ahead and swap row 1 and row 3 and push this row that has this 1 in the pivot position into the top. The reason why I like to swap rows containing ones into the top is that it makes it much easier to scale the rows to create canceling pairs. When we were dealing with this example and our pivot had something in there that was not equal to 1, something that was like -8, our scaling factor involved a fraction, which made the arithmetic a lot more complicated. So in order to avoid scaling by fractions, in order to be able to scale by integer values, I like to swap the rows around so that there is a 1 in the pivot position if possible, because it just makes the arithmetic easier. So now that I've shuffled a 1 into this top left pivot position, let's go ahead and try and eliminate the pivots underneath that 1. And eliminating the pivot in the second row is pretty straightforward because these two entries are already opposites. So immediately when we add row 1 into row number 2, that entry in the first position there will cancel out. So let's go ahead and do that. Add row 1 into row 2. So copy paste everything except for row 2, who is being modified. If I take row 1 and I add it into row 2, that's going to take this 1 and add it to this -1, and it's going to give me a result of 0 in that position. The next thing that I'm going to do is I'm going to add this 1 in the second column to this 0. So that's going to give me a 1 in this position. Then I'm going to add this 10 and this 7. That's going to give me a 17. And then I'm going to add this 4 and this 5, and it's going to give me a 9 in that entry. So I've eliminated the pivot from underneath that 1 in the second row there. The next thing that I want to do is eliminate this -3 in the third row of the first column. To eliminate this -3, I'm going to scale the first row by a factor of +3, +3 so that I get a +3 here, which will cancel the -3 in the third row in that position. So just to comment my steps here, scale row 1 by +3, then add into row number 3. So let's see what happens when we perform that action. Copy paste everything except for the third row, which we are modifying. So if I take number 1, the number 1 times +3, the result of that is +3, added to -3, result 0. If I take this value 1 and I multiply it by positive 3, that's a result plus 3. Add it to negative 5, the result is minus 2. If I take this 10 times this positive 3 and add it down into this 36, the result of that is 66. And if I take this 4 times positive 3 and I add it to 10, that's 12 plus 10, that's 22. This entry 1 is a pivot in the second column. So I would like to cancel out and eliminate the minus 2 underneath that 1 in that position. So friendly reminder, just so that we never get too far away from the point of what it is we're doing here. What has essentially happened is we have eliminated the x's from this system of equations by canceling out the pivots in the first column. What we're now working on doing is eliminating the y's. Having eliminated already the x's, now we are working on eliminating the y's. So to that end, I'm going to take row number 2, and I'm going to scale it by a factor of positive 2. Positive 2 because it's going to turn this 1 into plus 2, and that's going to cancel out this minus 2. Once again, because we already have achieved zeros in the first column, those zeros will not be modified or disturbed by this action that we're taking now. The entry right underneath the 1 is going to be canceled out by design. So then let's figure out what's happening with the third column and with the fourth column. So in the third column, we have 17 times 2 plus 66. So 17 times 2 plus 66 is 100. Amazing. 9 times positive 2 added to 22. I think that's 40. So with this step concluded, now let's take a step back and look at our matrix. So we can see that the matrix that we have just obtained is currently in row echelon form. So these are the basics of Gaussian elimination, and this is the process of doing Gaussian elimination by hand. Now, I confess, I don't think it's ever authentic. Like, I don't think in the real world you are ever doing Gaussian elimination by hand. You are always using some kind of computer software to do Gaussian elimination for you. Because as you can see, it's pretty tedious, right? It's a lot of arithmetic, sometimes fussy arithmetic involving fractions. And so this is not really something that we want to be doing by hand very often. Now, with that said, I don't necessarily want you to have to buy a graphing calculator if you don't have one already, because I do know that they can be expensive. So for the purposes of computation tests, in-class tests, I will give you matrices that are relatively small and easy to work with so that you can do Gaussian elimination by hand if you cannot afford to buy a graphing calculator. However, if you do have a graphing calculator, there are ways to use that graphing calculator to do Gaussian elimination automatically. The specific steps that you need to take on the calculator do depend on what type of calculator you have. Whatever calculator you happen to have, feel free to just go out to Google and ask it to show you how to do Gaussian elimination on whatever is your calculator. Okay, so to recap, today we introduced some terminology and an algorithm. We introduced the terminology of a pivot of a matrix. A pivot of a matrix is just the first non-zero entry that you encounter when you look into a row of a matrix. We also introduced the terminology of row echelon form. A matrix was in row echelon form if rows containing only zeros have been swapped into the bottom of the matrix, and if it has the property that pivots of each row move to the right as you move down the rows of the matrix. Row echelon form is meant to capture the appearance of the augmented matrix for a system of equations after you have worked through the process of eliminating the variables. So row echelon is just capturing what the augmented matrix looks like after that process has been completed. Similarly, this algorithm that we call Gaussian elimination is just the method of elimination that we learned in the previous video, except instead of applying those steps to the actual system, you apply those steps to the augmented matrix that represents the system. So that's all Gaussian elimination is. Gaussian elimination is the method of elimination as applied to the system's augmented matrix. In subsequent videos, we will talk about how to use this reduced matrix to recover the solution to the system of equations that we might have been working with in any particular problem. Like if you get this as the result of row reducing your augmented matrix, what does that tell you about these solutions to the system in your problem? We will talk about that in the next episode.